decide that we're going to put a polynomial over another polynomial, such as example 1, in a pretty simplified form, this is when we call it a rational function. Please note we have to be super careful because we know that we never can divide by 0. We never can divide by 0. So there are going to be limitations to our domain. Remember way back at the beginning of the semester when I said we're learning domain and it's never going to go away? Here it comes again. So our first examples are to find the domain of the following rational functions and write them in the form where I have a polynomial over a polynomial, and then simplify. When I'm looking at 2x minus 1 and x plus 1, this is already simplified for us because we can't factor anything and we're not able to simplify because we don't have any common factors in order to cross them out. But what we are concerned about is that the denominator cannot be 0. So our denominator is not allowed to be 0. So I want to say, well, what plus 1 equals 0? You probably could do this in your head. We know that x then cannot be -1 because when it is -1, we would have a 0 in our denominator. So when I'm looking at my graph here, notice how my red line for my graph is getting very close to -1, but it's not going to actually touch it. Our domain then, since that's what it's asking for, our domain starts all the way at -infinity and we're going to come across -1. And I'm going to put a parenthesis because it cannot be -1. I'm going to hop over, so I'm going to put a union -1 all the way to positive infinity, because then we get to continue on without any issue. Of course, it's going to get more complicated, and this can't just stay this nice and easy for us. So let's head over to slide 2. Here we have 2 minus 3 over x plus 1. When I'm looking for the domain, we'll simplify here in a second because notice the directions said to find the domain and then simplify. That will be very important as the problems get more difficult. So we'll find the domain and then we will simplify. So I'm going to find the domain. We already found the domain on the previous page when we had x plus 1 in the denominator. We can also see that this is true here with this problem. So our domain will still remain the same. Oops, if I could just spell it instead of trying to make it. We'll say domain is from -infinity to -1 parenthesis because it's not included. Union from -1 to positive infinity. But now we need to simplify. Well, to me this looks simplified, right? Why do we have to make it more complicated? But we want to combine our two parts together. Right now we have 2 over 1, even though we don't see it. We have 2 over 1. We want to combine these to make it one fraction. So to do that, we need to have a common denominator. So our lowest common denominator between 1 and x plus 1 has to be x plus 1. So just like if we were to add or subtract regular fractions without having a variable, that means that I'm going to then multiply the left-hand side by x plus 1 over x plus 1. I can distribute my 2 here. So I have 2x plus 2 over x plus 1 minus 3 over x plus 1. Well, now that we have a common denominator, we can continue simplifying. I have 2x minus 0x, so I'll still have 2x. And then I'll have 2 minus 3, and 2 minus 3 is -1, all over x plus 1. So I've found the domain first. and then we simplified. Let's head over to example 3 on slide 3. They're slowly getting a little more difficult. When I'm looking at my denominators here, I do see that they have the exact same denominator. But when I'm looking at my denominators, I am able to factor those denominators. We have a difference of perfect squares. So its factored form will be x plus 1 and x minus 1 for both the left side and the right side, since they are the exact same denominator. So again, it was a difference of perfect squares to factor them. Then we can look at the denominators and we can identify what our domain is. So when I'm looking at x plus 1, we already know that x cannot be negative 1. And when I look at x minus 1, we know x can also not be positive 1. Because in either case, we would end up with a 0. And if one of them is 0, the whole thing goes to crazy because it's multiplied by 0, which is still 0 in the denominator. So when I'm writing my domain here, I want to skip both negative 1 and positive 1. We're still going to go from negative infinity to negative 1. We're going to hop over negative 1. Our next piece then is going to be at positive 1, is how far we can go. And then we'll skip over positive 1 and continue to infinity. But you're saying in my picture here, I only see one part that we're skipping. We're going to see here in a second what's going to happen when we do the numerator. Once we start simplifying, something else is going to happen that will be important. When I'm looking at my numerator then, I can now subtract, so I can create one solid fraction because they both have the same denominator. We're able to just simply move into the subtraction portion. I have 2x squareds. I have 0x squareds that I'm subtracting, so I'll still have 2x squared. I'm going to do my x values first. So notice on the left I have 0 x's. So if I have 0 x's and I subtract 3x, I'm going to have negative 3x. And negative 1 minus negative 2 turns into a positive 1 over x plus 1, x minus 1. I'm going to leave it in factored form because what if we are able to simplify once we have our numerator in factored form? Because I have a value in front of my x squared, we're going to have to factor by using the AC method, where I want to find two numbers that multiply to 2 times 1 because there's that number in front of x squared, but yet adds to negative 3. So two numbers that do multiply would be negative 2 times negative 1. And when I add them together, negative 2 plus negative 1 is negative 3. The next part of the AC method is that we split our middle term utilizing those our perfect numbers that we found. And now that I have 4 terms, we're going to continue by factoring by grouping. So I'm going to group the first 2 together and the second 2 together. I see the first 2 are both divisible by 2x. And when I factor out 2x, I'm left with x minus 1. I can also factor out a negative 1 from my second pair. And when I factor out negative 1, I'm left with x minus 1. Notice that our x minus 1s are the exact same, so I will factor out the common factor of x minus 1, leaving us with 2x minus 1. And my denominator is still x plus 1, x minus 1. Now another way to have factored the numerator, in case it's been a while since you've done that technique, another way you could have done was the guess and check. So guessing and checking factors until you found the right combination. Notice then in our numerator and our denominator, we have a common binomial factor, the x minus 1s. These can simplify because we are in multiplication and I'm multiplying the two binomials together, which allows me to then eliminate that common factor. So when I'm simplified then, our solution, our simplified function is 2x minus 1 over x plus 1, which is why we only see the one asymptote here on the left. But what about this other domain, this positive 1 that we're skipping? Because we were able to cancel out that common factor, that tells me that when x is equal to 1, in this case right here, that tells me it's going to give me a hole at that graph. So if I were to have put my pen over that utilizing Desmos, it would have said 1 undefined. So because I canceled it out, that is where that other part of the avoided domain we ignore is, because of where we're able to cancel out the common factors. And we'll talk more about that in detail here coming up, so don't worry about that, but just showing you where they're coming from. Let's head over to slide 4. We can continue to simplify. This one looks a little weird, a little bit of a weird graph. So it says to find the domain before we simplify, in case we need to worry about holes. If I were to have simplified and then found the domain with that last example, you may have only thought that we should skip over -1. You may have missed the positive 1 to skip over. With number 4 here, I'm going to rewrite this as 2x squared minus 1 over x squared minus 1 and use our old traditional division of 3x minus 2 over x squared minus 1. Because we have two denominators we need to worry about, which seems kind of strange. We have the denominators of x squared minus 1, so we already know from the last example that x can't be 1 and x can't be positive 1 from those denominators. But notice this top fraction is the entire numerator and this bottom fraction is the entire denominator. So we have to worry about 3x minus 2 over x squared minus 1. Where is this equal to 0? Because we are going to have to look at a place where this can't be 0 either. So where is 3x minus 2 over x squared minus 1? Where is this equal to 0? Because we want to avoid this denominator being 0 as well. Well, to solve for x, we would multiply both sides by x squared minus 1. So that our denominator will be eliminated, leaving us with 3x minus 2, still equal to 0, since 0 times anything is 0. Now it's not too bad to continue solving. 3x is 2, and x is equal to 2/3. So we also want to make sure that x is not equal to 2/3, so that we cover the entire denominator over on the bottom here is also not equal. So when I'm looking for the domain then, we know we're going to come all the way from negative infinity to -1. We'll go from -1 to 2/3, since 2/3 is smaller than 1. 2/3 to +1. And 1 to infinity. So a 4-part series finding the domain. Now let's actually simplify. I'm going to start off with 2x squared minus 1 over x squared minus 1. We know that to divide fractions, we've been drilled to reverse and multiply, or don't ask why, just reverse and multiply, or keep, change, whatever rule that you have memorized over the years, that we turn division into multiplication and then flip over that second fraction. At this point, we can certainly see that we have a common factor in the numerator and denominator, which is eliminated. So that our simplified form is 2x squared minus 1 over 3x minus 2. So it's interesting that at positive 1, which we can't see on the graph, and negative 1, there would be holes there. And positive 1 we can't see, it's going to be way down below here. Theirs would be holes because we canceled off the x plus 1, x minus 1 portion. And also, 2/3 here is where this part comes into line. So it's kind of hard to see, but it is there. You're also going to notice that it also probably has a slant asymptote that we're getting close to. We'll talk more about that on Tuesday with slant asymptotes. Let's head over to slide 5, where we're going to actually start defining some pieces here. In that first example, we know our graph is undefined at x is -1. So what happens to our graph as we approach -1 from the left side of the graph? And what happens to our values as we approach -1 from the right side of our graph? Notice then I used a table of values on the left-hand side there. So we are approaching -1 from the left side of the graph. So notice that they're getting smaller and smaller, but yet closer and closer to -1. And here I am approaching -1 from the right side, so my values are larger than -1. Notice what's happening to our y values as we're going in either direction. So to put this more specifically, we'll do it up here. As x is approaching -1 from the left, so as x is approaching -1 from the left-hand side, notice that our y values are getting bigger forever. So when I have the negative piece here with my x, this means I'm approaching from the left-hand side, from the negative side of -1. F of x, so our y values are approaching then positive infinity. Now, if I'm looking at approaching -1 from the right-hand side, so as I'm coming from negative infinity, so from the right-hand side as I'm approaching -1, I'll report this as x is approaching -1, positive, so from the positive side of -1, notice what's happening to our graph. Our y values are approaching negative infinity. So f of x, our y values are approaching negative infinity. Similarly, I have this exact same graph. Notice we also might have a horizontal asymptote, and we're going to talk specifically about how we know and how we obtain what those values are. I'm just kind of going through some information before we get to more specifics. So looking at the graph on the right-hand side, notice what happens as x is approaching positive infinity. What is happening to our y values? Also, as x is approaching negative infinity, what is happening to our y values? So let's start with positive infinity. So as x is approaching positive infinity, so as x is going to the right forever and ever and ever, notice our graph is getting closer and closer to 2. That tells us that as x is approaching positive infinity, our function values are approaching 2 from underneath of it. So that negative means I am approaching it from underneath that asymptote. Versus as x is approaching negative infinity, our function values are still approaching positive 2, but notice they're approaching positive 2 from the top. So 2, and then in their exponent, if you will, 2 from the top, so the positive side. I'm going to have many more examples, so if that was a little overwhelming, I'm going to have many more examples explaining each of these notations in the upcoming examples. So let's head over to example 6, or slide 6, I should say, where we define a vertical asymptote and a horizontal asymptote with respect to utilizing the values as it's approaching a value. Our function is going to either positive or negative infinity. And horizontal asymptotes is looking at as x is approaching positive or negative infinity, our function values will approach a specific number. So the two different formats that we have. And when we look back at that second example that we talked about, notice how when I put it into Desmos and I rolled my pen over that one value, we ended up with a hole in the graph. And that's really, I mean, it is just called a hole. It happened because we were able to eliminate the factor. So only when you are able to eliminate a factor is that when a hole is going to appear. Let's look at more examples on slide 7. How can we determine when we have a vertical asymptote? So let's suppose that we have a rational function. Remember, a rational function is just when we have a polynomial over a polynomial where there are no common zeros. Then we have two options that happen. There will be a vertical asymptote if that value is given a 0 in the denominator. If it's not a 0 in our denominator, then there might be a hole in the graph when we are able to eliminate it. So let's find the vertical asymptote of and or holes in the graph of the function below. And it'll say in your homework too to verify using a graphing calculator. So I certainly recommend Desmos because I like that you can hold your mouse down and drag your mouse over the graph, and you'll see that will say a value that's undefined, and it'll put the hole there. You won't see it just looking at it. You'll have to put your marker or your cursor over the graph itself to identify those pieces. All right, let's look at 2x over x squared minus 3. So when I first need to find the domain in order to identify where there may be asymptotes in our graph, I want to know when will my denominator equal 0, because those are the places I want to avoid. So when will x squared minus 3 equal 0? Well, I can add 3 to both sides, and then I can take the square root. So I will have x is equal to positive or negative 3. We know then that x cannot be positive square root 3, and it also cannot be negative square root 3. Notice that even though I'm able to identify where my values cannot be 0, I'm not able to actually simplify my my rational function, because there's nothing to eliminate. So let's look just solely then at our domain. Our domain is going to be from negative infinity to negative square root 3, parenthesis, because if we did include the square root of negative 3, we would have a 0 in the denominator, and we can't have that. Then we'll go from negative square root 3, our next value would be positive square root 3. We need to skip square root 3 and then continue to infinity. Since we are not able to cancel anything, we have no holes in the graph. So I'll just make a note that we did not, we had no cancellation of common factors. So there are no holes. Notice then that these x values, before we simplify, these will be our asymptotes. We have vertical asymptotes. At x is equal to the square root of 3 and x is equal to negative square root 3. It's kind of hard to, since it's a weird decimal, we can see that our graph is approaching those two places, but not actually going to touch them. I can easily then describe the graph, because notice it says describe the behavior of the graph at those locations. So this is where we're going to utilize as x is approaching this is what's happening. Let's start with, I'll use a different color. Let's start with our negative square root 3 asymptote. So as x is approaching negative square root 3 from the left, so as x is approaching the negative square root 3 from the left hand side, notice that our y values are getting negative. Our function values are approaching negative infinity. Also, as our x values are approaching negative square root 3 from the right hand side, so negative square root 3 and then a little plus in the top right corner, our function values then are approaching positive infinity. Let's look at our asymptote for square root positive 3. So as our x values are approaching positive square root 3 from the left, so as x is approaching positive square root 3 from the left, our function values are approaching negative infinity because they're getting smaller. So f of x is approaching negative infinity. As x is approaching square root 3 from the right hand side, our function values are approaching, our graph itself is approaching positive infinity. Okay. Let's check out another example. Maybe this next one on slide 8 will have a vertical asymptote with holes. I have on this slide also the definition in case you need to see that and kind of put the pieces together. Let's first look at our domain. I can factor my denominator, and when I factor my denominator, it is a difference of perfect squares, providing us with x plus 3, x minus 3. In our numerator, I want to find something that multiplies to -6 and adds to -1. -3 times 2 will give me the proper parts. When I write them in factored form, we'll have x minus 3, x plus 2. We didn't have to use the AC split method if you're questioning that, because the number in front of x squared is 1. Only when the number is larger than 1 do you have to do the AC split method. When I'm looking at my denominator though, I know that my domain cannot be, so x cannot be -3 or +3. So if I'm thinking about my domain, we'll have -infinity to -3, -3 to +3, and then finally 3 to infinity. I know it didn't say to find the domain, but it doesn't hurt to practice. But check this out. Now that it's in factored form, we have a common factor in our numerator and in our denominator. Now, because we canceled something out, we have a whole. So since we canceled it out, we have a whole at +3 something. We have a whole at +3 something. How do we determine where that whole specifically is located? I'm going to evaluate my function at 3 using the reduced polynomial after I've gotten rid of my canceled part. So the only thing left in my numerator is x plus 2, so 3 plus 2. And in our denominator, we'll have 3 plus 3, or 5/6. 5/6. So that is specifically where we can find it, utilizing the reduced rational function. That is where we're going to evaluate it at. So we do have a whole. We have an asymptote at, I hope that's -3. Yeah, that looks like it should be -3. Where we can evaluate this as x is approaching -3 from the left-hand side. Notice our y values are getting more positive. So our function values are approaching positive infinity. But as x is approaching -3 from the right-hand side, our y values are approaching -infinity. Let's take a look at slide 9, where we talk about horizontal asymptotes. There's 3 pieces that we need to consider when talking about horizontal asymptotes. When talking about horizontal asymptotes, we want to look at the degree, the original degrees of the polynomials that we have. So if the degree of the numerator is the same as the degree of the denominator, then our horizontal asymptote will be a over b, where a is the leading coefficient of the top and b is the leading coefficient of the bottom. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is automatically y equals 0. And if the degree of the top is bigger than the degree of the bottom, there are no horizontal asymptotes. So looking at f of x is equal to 5x over x squared plus 1, Here it's asking us to just find the horizontal asymptotes and then describe the behavior as it's approaching using our proper notation. So we don't actually have to simplify to look for the horizontal asymptotes. Notice that the degree of our numerator is 1, so the degree of p of x, our numerator, is less than the degree of the denominator. Since the degree of the numerator is 1 and the degree of the denominator is 2, we fall in line with the second bullet that automatically the horizontal asymptote is y equals 0. And we can see that that's happening right on our graph here. It is okay for your graph to go through a horizontal asymptote. With the last examples, notice we got really close to the vertical asymptotes and we would never actually touch it. It is okay for a horizontal asymptote to go through our graph itself. There's nothing saying that it cannot. But let's talk about how we're looking at the graph itself and writing it in proper notation, the behavior that the graph is taking on. So as our x values are approaching negative infinity, so as we're getting smaller, notice that our graph is coming up on y equals 0 from the bottom. So f of x is approaching, our function is approaching 0 from underneath, so from the negative side. And as our x values are approaching positive infinity, our function values are also approaching 0, but notice they're approaching 0 from on the top side of 0. One more example. Let's see how this works. Here we have x squared minus 4 over x plus 1. So when I'm looking at my numerator, I notice that my numerator has a degree, so p of x has a degree of 2, and q of x has a degree of 1, and we know that 2 is greater than 1. So since 2 is greater than 1, the graph has no horizontal asymptotes, and we can see that it's really not approaching that anyways. So no horizontal asymptotes. But since we have a couple of minutes, we can look at potentially finding a vertical asymptote when our denominator is not, or would be equal to 0. So we do have a vertical asymptote when x is equal to -1, because that would mean that we would have a 0 in our denominator. We're also not able to simplify or cancel anything, so we also know that there are no wholes since we had no cancellation of common factors. We simply have the vertical asymptote. So one more time, we'll talk about the as x is approaching from the left and the right, just to have one more example. I don't think it would hurt to have too many. So as x is approaching our vertical asymptote from the left-hand side, our y values, g of x, I should say, g of x is approaching positive infinity. At the same time as our x values are approaching -1 from the right-hand side, our function values are becoming more negative. So they're approaching negative infinity. In your next lesson for the next class period, you're going to talk about slant asymptotes. They're also known as oblique asymptotes, where they're on a diagonal. And then I will also go over examples for how you find all of the asymptotes with holes, showing you multiple examples of putting it all together.